Hello, 171 class. This is your part 3 of your notes for section 7.1. So what we're dealing with now is not every single system of equations will have just that one unique solution like we've been doing, that one ordered pair where they cross. Two lines could never cross. They could be parallel lines and never intersect. Or, notice this is blue, this is red. If a blue and a red sit on top of one another, we're looking at it, we would see purple. Alright, so what we're saying here is that every single point here is lining up. And every single point that's on the one line is also on the other line because the 2 points, the 2 lines are identical, they're the same line. So in that case, everything that's on one line is on the other line, so there's infinitely many solutions. So we can have one, we can have none, or we can have infinite number. Okay, there's no way we can have just 2, or no way we can have just 4 or 7. It's either 1, none, or infinite. Now we have to understand too that an infinite number of solutions does not mean all real numbers like what you may be used to when there's more than one solution to an equation. Alright, when we have an equation like 2x plus 2 equals 2 times x plus 1, the solution to that is all real numbers. Everything works because we only have that one variable. And we use that symbol to represent all real numbers, meaning that there's an infinite number of solutions and every single number works. But that's not the case with systems, 2 by 2 systems. For instance, this point right over here. That's not on either line, so that point doesn't work. So we can't say all real numbers. We have to say infinitely many solutions. And when we get to it, I'll show you how to write what the infinitely many solutions are. But it's not what you may be accustomed to writing, the all real number symbol. That does not apply when there's more than one variable. We can't just say all real numbers work because in this case they don't. All real numbers don't work. Or all ordered pairs of real numbers, that I should say, don't work. Alright, so let's solve the system. Let's look at this thing. We got 4x plus 6y equals 12, 6x plus 9y equals 12. So I'm going to pick a method to solve this. The method I'm going to pick, if I don't have a variable that's easy to isolate or solve for, I'm not going to use substitution. So in this case, I would use the addition method. And I'm going to multiply the top equation by 3, because that'll give me a 12x. And then I'm going to multiply the bottom equation by negative 2. That'll give me a negative 12x. So distributing this 3 to every part of the top equation and the negative 2 to every part of the bottom, I get 12x plus 18y equals 36 for the top. Negative 12x minus 18y equals negative 24 for the bottom. And notice now when I add, when I get the sign change that I was looking for with just x, I also get a sign change for y. But when I add, there's nothing for x, there's nothing for y, there's literally nothing left on the left side when I add those two equations. But on the right side there is. 36 minus 24 is 12. So I get the equation 0 equals 12. But 0 is not equal to 12. Okay, that's not true. So what this says is a linear system with no solution is called inconsistent. If you attempt to solve such a system by substitution or addition, we used addition, you will eliminate both variables. X is gone, now y is gone also. And then a false statement like 0 equals 12 will be the result. So 0 equals 12 is not true. It's never true. 0 can't be equal to 12. So this system can't have a solution. So this is an inconsistent system, which means no solution. And it's fine to put the little no solution symbol, which is an empty set symbol, 0 with a line down through the middle of it. Alright, but remember, 0 equals 12, if it isn't true when the variables get eliminated, then you have no solution. Alright, now let's attempt to solve this system. This one does have a variable isolated, so I could do one of two things. I could bring the 3x over if I wanted to do the addition method, but because y is already isolated, this is where I would use substitution. So y is isolated, so I can substitute that in for that y down there in the other equation. Alright, again, I'm told y, this y right here and this y are the same because of the fact that they have to be equal at the same time. And this y is equal to 3x minus 2. So is this y. Alright, this is where that y was. So I'm just replacing the 3x minus 2 there with it. Alright, and now I'll just go through and solve. So first I'm going to distribute the negative 5 through. So when I distribute that through, I get negative 5 times 3 is negative 15x, and negative 5 times negative 2 is positive 10. The 15x cancels, so I'm left with 10 is equal to 10. Now what this says here is if a linear system that has at least one solution, we consider that a consistent system. So if they do cross one time, then that's a consistent system. But if they cross more than once, if they coincide, meaning they're the exact same line sitting on top of one another, that's still a consistent system. All right, but if they coincide and it has infinitely many solutions, we call that a consistent system that's dependent, all right, or a dependent consistent system. So if you attempt to solve and all your variables get eliminated, so we eliminated y here by the substitution, there's no y left. But then going through and doing the work, we also eliminated x right here. There's no x's left. And you're left with a true statement such as 10 equals 10 like we had. Then that means that this is a dependent system where there are infinitely many solutions. There's more than one solution. Right? But like we discussed here, it's not all real numbers. Like a point right here is not a solution. Only the ordered pairs that would fall on the line are the solutions. What we say in that case to write the solutions of the system, we would say the set of all the ordered pairs such that the y coordinate is equal to 3x minus 2, which is just one of these original two equations. Or we could say the set of all ordered pairs such that the second equation, 15x minus 5y equals 10. As long as we write either of those two equations, it's fine, and that expresses our solution. What we're saying is all the points on this line, or it's all the points on this line because of the exact same line. So we are getting the same exact line when we express it in either way. So if you go through your work and all your variables cancel and you're left with a true statement, that's a consistent dependent system. But if you go through your work and you're left with a false statement, then that is an inconsistent system. There is no solution. All right, these are parallel lines. These are lines that line up one on top of the other. All right, quickly I want to show you how to do these on your calculator with that matrix menu when we have no solution or infinitely many solutions, an inconsistent system or a dependent system. So what we're going to do here is go into the matrix menu, type it in just like we did before. So edit 2 by 3 and then type in our numbers. So 4, 6, 12, 6, 9, 12. Alright, and then we're going to back out, second quit, back into the matrix menu, math, look for RREF, and then back in second matrix A, and then enter. Okay, now if you have decimals, especially if it's a repeating decimal that goes off the screen, you can always press math 1 into a fraction and change those decimals to fractions. Okay, but this was still on the screen, so we could have easily seen it. But the point is, what I want to highlight here is a lot of people want this, you know, they just go straight to this no matter what. But really, the reality of it is, if you use the matrix menu, the very first thing you need to look at is the bottom row. All right, remember this bottom row is an equation, and this is saying 0x plus 0y is equal to 1. Nothing is equal to 1. Now we got 0 equals 12 here. All right, but it will always go through and divide this by whatever number it is and give you a 1. But if you see two zeros followed by a 1, that's saying that 0 is equal to 1, which is not true, which means there's no solution. So when you use this matrix menu on the calculator, you need to train your eye to go down to the bottom row so you know what you know if this is the solution or not. If you see zeros and then a 1, then this is not the solution. There is no solution. 0 can't be equal to 1. So you've got to train your eye to go down here to that bottom row first before you even look at this right-hand column. All right, now let's look at one that's got a dependent system. Now, remember, if you're going to use the matrix menu on the calculator, you have to have that ax plus by equals c look, like the bottom one does, but the top one doesn't have that look. So what I'm going to have to do here is I'm going to have to take the top equation and I'm going to have to move the x over to join the y. And I'm going to rewrite that as negative 3x plus y equals negative 2. Okay, and remember this is a 1y. So now when I go to the matrix and I edit this thing, this top row I don't put 1, 3, negative 2. You got to have it in this form. So we put in negative 3 for x, 1 for y, and then negative 2 for the constant. Okay, it's got to have this look to it. The bottom one's already in that look form, so I just type in it as it is. But the top one we did have to alter. If you're going to go into the matrix, you have to have it in that ax plus by equals c form. All right, got it in. So second mode to quit, math, RREF, second matrix 1 again. Again, I could have just hit enter since it was the last thing I did. So again, to see it goes off the screen. If you have repeating decimals, remember press math 1 for changing it to a fraction. Now everything's nice and tight again back on the screen. So don't fall into the trap of looking right here and thinking that's your solution, 2/3 and 0. That's not. Okay, look at the bottom row. There is a 0x plus 0y equals 0. 0 equals 0. Now here again, when we did the work by hand, we got 10 equals 10. That's true. That's a true statement. So we had a dependent system. Here we have 0 equals 0. That's also true. 0 does equal 0. So even though we're not getting the same thing we did when we did the work, we're still getting true statements when it was true. We were getting false statements when it was inconsistent. So make sure that you are understanding to look at this bottom row. 0, 0, 0 is a dependent consistent system. 0, 0, 1 is an inconsistent system with no solution. So you can still use your calculator and identify consistent systems, inconsistent systems, and dependent systems. You just have to know, look at the bottom row first, then look column-wise. What you're ideally going to see, and if there is just a single solution, you'll have 1, 0, a number, 0, 1, a number. But if this bottom row is 0, 0, and then anything here, you're either going to have an inconsistent system or a dependent system like we see here.